Cosmology is defined by NASA as the scientific study of the large-scale properties of the universe as a whole. Let's have a look at some of these theories about the overall structure of the universe, its origin and evolution. Something that's puzzling cosmologists is the fate of the universe. This can be determined by its curvature. Curvature, symbolized by the Latin letter K, is the amount by which a plane deviates from being flat. In simple terms, it is how curved a space is. Depending on the value of K, there are three possibilities for the shape of the universe. These are known as Friedmann universes. A flat universe corresponds to zero curvature and means that in a flat space, the standard laws of Euclidean geometry apply. These include the principle that the sum of the vertices of a triangle equals to 180 degrees and the fact that parallel straight lines do not converge or diverge, but instead the distance between these lines remains unchanged as the length becomes infinite. In an open universe where the curvature is negative, these laws don't apply, but instead, non-Euclidean hyperbolic geometry comes into play. Imagine a hyperboloid. If you draw two parallel lines, they will diverge from each other instead of remaining parallel in the sense that we understand it. And if you now draw a random triangle, the sum of the vertices is less than 180 degrees. The last case is a closed, positively curved space, pretty much like a sphere. The geometry that underlines the previously mentioned features on a sphere is known as spherical or elliptical geometry, and here the sum of the vertices of a triangle is greater than 180 degrees, and the parallel lines converge. However, we can only observe a small fraction of our universe, the so-called observable universe, which makes it difficult to be confident about our conclusions when it comes to the shape of the universe as a whole. Cosmologists need alternative ways of determining the curvature. One method is concerned with measuring the matter density within the universe. But how is density associated with curvature? Einstein's theory of general relativity demonstrates the gravitational effect of matter curving space on small scales, which indicates that the shape of the universe is controlled by the density of matter within it. For a flat universe, the average density of matter is called critical density and is the density that is enough for the universe to just hold its expansion after infinite time. If, however, the average density of matter in the universe is lower than the critical density, the shape of the universe corresponds to the open model. In this case, self-gravity is insufficient to stop the expansion, and the universe continues to expand for infinite time. This could either lead to a big freeze, where as the universe expands, it cools down until everything is at the same temperature and nothing happens anymore, or a big rip, where matter and even space-time itself get ripped apart by the expansion. The last possibility is that the density is higher than the critical density, and self-gravity slows the expansion until the universe holds and ultimately recollapses. The Big Crunch scenario. This is the case for a closed universe. This concept is mathematically represented by the cosmological constant, also known as the density parameter. Symbolized by omega naught, the density parameter is the ratio of the average density of matter to the critical density. If omega naught is exactly equal to 1, then the universe is flat. If omega naught is less than 1, the universe is open, and if omega naught is greater than 1, the universe is closed. we can see that measuring the density of matter within our universe can unveil its fate. But measuring this mass is no simple task. Omega naught corresponds to the total density of matter. Therefore, we have to question if the observable density is also the actual total density. After years of research and analysis of data gathered from our universe, it was found that the total density parameter is determined by the following formula. The total density parameter equals the mass density of baryonic matter and dark matter plus the effective mass density of relativistic particles like photons plus the effective mass density of an elusive force called dark energy. There are still many unknowns in cosmology. As just mentioned, dark energy is one of these mysteries. It is also still uncertain what geometry our universe has. Let us know what you think by voting in the poll in the top right corner, and stay tuned for the next UCL Physics Filmmakers video.